Assalamu alaikum. Welcome to the 11th International Conference on Electrical and Computer Engineering 2020. This is Abul Kalam Azad presenting numerical analysis of Mach-Zehnder interferometer based optical sensors incorporating WGM ring resonator. My co-authors are MD Johirul Islam and MD Rizvi Kaisar. Outline of the presentation: motivation, objectives, optical sensor, modeling of MZI incorporating ring resonator, modeling of ring resonator, numerical results, comparison of sensitivities of MZI based sensors, and conclusion. Motivation of the research: the technique of calculating concentration or refractive index like refractometer, fluorescence measurement and Brewster angle minimal variance has many limitations such as complexity of manufacturing, bulky size, requiring costly equipment, and depends on visual and subjective data measurement. Otherwise, optical sensors are tiny in size and are used in diverse for sensing of various physical phenomena such as gas or liquid flow, displacement, temperature, pH, health condition of the breeze, and the MZI is teeny and highly sensitive. As the target biological particle interacts with the incoming light in the WGM ring resonator, the WGM ring resonator based MZI sensor facilitates both spectral and phase response. Objectives of the research: evaluating MZI's performance by including ring resonator, optimized design to get high sensitivity, performing phase and wavelength sensitivities. Sensor: a transducer that converts physical quantity into measurable one. Optical sensors are a wide class of light intensity measuring instrument, and electrical output is provided by most optical sensors. The MZI based optical sensor consists of an optical waveguide with two reference and sensing arms. Modeling of MZI incorporating ring resonator. In the proposed MZI sensor, the sensing arm consists with ring resonator. The path length of sensing arm L is 14.56 micrometer and operating wavelength lambda is 1.55 micrometer. As the sample solution varies 1.3 to 1.4 refractive index, the change in the refractive index del n is 0.1 and the change in effective refractive index del n is EFF is 0.0258 and the change in resonance wavelength 30.7 nanometer. So that the phase difference is del phi and S lambda is wavelength sensitivity and S phi is phase sensitivity. Modeling of ring regenerator. The ring regenerator parameters of MZI sensor are: core width is 0.2 micrometer, cladding width is 2.1 micrometer, radius of curvature is 6.230 micrometer, separation between bus core and ring core is 450 nanometer, cladding and core refractive index 1.2 and 1.34007 respectively. The core refractive index of buses varies from 1.3 to 1.4. The light that passes through the straight waveguide couples to the ring, and therefore resonance can occur, which must satisfy the following condition: M lambda res equal 2 pi r n EFF, where indicates M is resonant mode, lambda res is resonance wavelength, and capital R the ring radius in micrometer, and LEFF effective refractive index. Numerical results. Figure 1 shows the electric field distribution in the resonator at the resonant wavelength of 1.470833 micrometer, and the corresponding transmittance spectrum for a ring resonator at this resonant condition is shown in figure 2. The resonance wavelength, green color, shifts according to the change in refractive index from 1.34 to 1.33. Figure 3a shows the variation of resonant wavelength shift with the change in analyte's refractive index, and it increases with the increase in analyte's Ri. The wavelength sensitivity was calculated using equation 2, which is found to be 307.0 nanometer per refractive index. Figure 3b shows the phase change with the change in refractive index of analyzed solutions. The phase difference was calculated using equation 1, and phase sensitivity was calculated using equation 3, which is found to be 4348 pi per refractive index. Comparison of sensitivities of MZI based sensor. A comparison of the proposed WGM ring resonator based MZI sensitivities with other different MZI technique are shown in this table. Considering both wavelength sensitivity and phase sensitivity, it offers good sensitivity. In wavelength sensitivities, it offers 307.40 nanometer per refractive index, and phase sensitivity 4348 pi per refractive index. Conclusion. In the conclusion multiphysics environment, the WGM ring resonator based MZI sensor system was successfully modeled, which is found to be 307.4 nanometer per refractive index in wavelength sensitivities and 4348 pi per refractive index in phase sensitivities. In future, this analysis will be helpful to design MZI based optical sensor such as hemoglobin, cancer detecting, glucose sensor. Thank you for listening.